Hello and welcome to ACM's fourth learning webinar. This webinar reflects ACM's deep commitment to lifelong learning. Our aim is to empower computing professionals and students who join ACM's worldwide community of 100,000 plus members. My name is Gary Olson. I am the Donald Bren Professor of Information and Computer Sciences at the University of California, Irvine, a member of the ACM SIGCHI Academy, and an ACM Fellow. I'll be serving as moderator for today's webinar. ACM offers innovative educational and professional development resources that bolster skill sets and enhance career development opportunities. Our members are able to stay competitive in the dynamic computing world with a range of ACM Learning Center online resources at learning.acm.org. You can see some of the highlights on your screen. ACM recognizes the role of computing in driving the innovations that sustain competitiveness in a global environment. Together with timely computing information published by ACM, access to the ACM Digital Library, the world's most comprehensive database of computing literature, and international conferences that draw leading experts on a broad spectrum of computing topics, ACM enables its members to solve critical problems using new technology that enriches our lives and advances our society in the digital age. I'm here representing ACM's Special Interest Group on Computer-Human Interaction, or SIGCHI, which in addition to cooperating in this event, is proud to publish Interactions magazine and sponsor a number of top conferences in the field, including the annual CHI Conference on Human-Computer Interaction, the CSAW Conference on Social and Collaborative Computing, and the RECSYS Conference on Recommender Systems. Both Joe and I have been very active in SIGCHI governance. Today's presentation is Recommender Systems, the Power of Personalization by Joseph A. Konstan of the University of Minnesota. Before we get started, I'd like to mention a few housekeeping items. At the end of our presentation, we will have time for questions, and we hope that you'll have several. Also, watch for live poll questions during the presentation. You can submit your answer when a poll is presented by clicking on the Submit button. In the top right corner of the slide area on your screen, there is a green button that will allow you to enlarge the slides. You may enlarge the slides at any time by dragging the corner of the slide window. The slides will advance automatically throughout the event. You can minimize the slide area, Q&A, and bio screens using the buttons in the bottom panel. If you are experiencing problems with the program, please press F5 on your keyboard if you are on a PC or Command-R if you are on a Mac to refresh your console or close and relaunch the presentation. You can also visit the webcast help guide by clicking on the Help widget in the slide window. Please disable pop-up blocking software so that you can receive and respond to the feedback form at the end of this presentation. To control volume, adjust the master volume on your computer. This session is being recorded and will be archived. It will be available for review in the next few days at learning.acm.org/webinar/recommender. If you think of a question during the presentation, please type it into the Q&A box on the lower left of the presentation screen and click on the Submit button. You do not have to wait until the end of the presentation to begin submitting questions. You may also use the Q&A box to suggest topics for future webinars of interest to you. And now I'd like to introduce our speaker. We are honored to have presenting today Joe Konstan, who is the Distinguished McKnight University Professor and Distinguished University Teaching Professor of Computer Science and Engineering at the University of Minnesota. He's published more than 50 research articles on the topic of this webinar and co-authored Word of Mouse, The Marketing Power of Collaborative Filtering, one of the first books on the application of recommender systems to commercial systems. Joe also holds 5 patents related to recommender systems and co-founded Net Perceptions, Inc., a company that commercialized recommender engines and has a variety of online and bricks and mortar companies, including companies like Amazon. Joe and his colleagues won the ACM Software Systems Award for their work on recommender systems. He is also a fellow of the ACM and a member of the CHI Academy. He chaired the first ACM conference on recommender systems and recently chaired the CHI 2012 conference. Joe, we look forward to your presentation here today.
Thank you very much. In the spirit of recommender systems, I'm going to start by asking all of you a couple of quick questions. You should have a first poll in front of you where we're trying to find out a little bit about your knowledge coming in about recommender systems. And in a minute, I'm going to ask you what you're trying to get out of this webinar, and we'll be dynamically adjusting the content to what I see coming in. And so we still have a few people getting results in here. So as soon as I get a few more of these, we will push that out to you. Okay, it looks like we're converging. So as we can see, we've got a bunch of people here who have used recommenders and are somewhat familiar with how they work. We also have a bunch of people who are not familiar with them at all. And so just to have at the very basic level, any of you who've used Amazon.com, whether you know it or not, have been using a recommender system. At the very basics, a recommender system is something that takes an overwhelming set of options that you might need to select among. The original concept was the information overload of too many choices, and uses some technology to pick the ones that are most likely to be of interest to you, most likely to be things that you would buy. And what you're looking at here in this screen of Amazon, I will come back to in a minute when we talk about some of the specific techniques for how these are used. But I do want to go to one more question, which is why you're here. And so if you'll just take one moment and let me know what you're looking for, and then we'll jump into the history of recommender systems and then examples and technology. Okay, this seems like enough to get a pretty good sense that a lot of people here are interested in the technology. We will probably use the second half of the time here focusing primarily on technology as a result of that, and I will keep case studies and examples in an introduction, but I'll make them a bit shorter. So when we talk about the history of recommender systems, I'd like to briefly start back about 20,000 years ago. And the idea, if you go back then, is that humans have became this wonderful, creatures that evolved to take advantage of the learnings of others. And so, classic example, you have a bunch of people living in a cave. They're all hungry all the time. And outside the cave, there's this plant growing with these bright red fruit on it. And the question is, do you eat the fruit? Now, those of us who've grown up with tomatoes might think that's a wonderful thing. They're tasty. We should try them. But you might also discover that there was the deadly nightshade, which looked a lot like a tomato and was remarkably poisonous. And the basic idea of sharing the information of others is that we would be a wiser and survive better as a people if one of us ate that fruit, and then the rest of us stand around and watch and see whether that person gets sick. Now, over time, we added science, we added technology, we added the concept of critics, people who had basically the job or the hobby of going around and trying out whether it was the tomato or the latest play or movie, so that we don't all waste our time and money doing it. And we all are pretty comfortable and familiar with the idea that we take the opinions of others into account as we try to figure out what we're doing for ourselves. If we move this into the space of technology, we have the whole field of information retrieval and filtering. And information retrieval specifically is all about taking a static content base, a library, a document archive, and investing in indexing that content base so that people can come in with a new need every time and present their query against that indexed document base. And that's not the focus of this webinar, so we won't go into the details, but those of you who are familiar with information retrieval may have seen the term TF-IDF, or term frequency, inverse document frequency, a basic mechanism that was quite innovative in leading to the idea that you could find things that are interesting to what you're looking for if you find things that match the terms you're looking for. They say that term a lot, but that the terms themselves are more informative if they don't appear in every document. In fact, if you go to a site like the ACM Digital Library, you can type in a query for recommender systems, and if you do that, it will come back and give you a bunch of articles that use the term recommender systems, have in this case recommender systems in the title, and you can start exploring from there. The flip side of that is information filtering, and that's where recommender systems really came most directly from. Information filtering changes the assumptions. It says that we're going to assume that you have relatively stable needs, but that the content is changing over time. So you're always interested in following what's going on with the Minnesota Twins baseball team, but new articles come out every 10 or 15 minutes, and you want to make sure that the ones that are about the Twins are articles that you read about. And so just as you flip the assumptions, the technology flips where you put the effort. You spend lots of time in building a profile, and in turn spend less time on the content so that you can pass your content through your profile quickly. And the same ACM Digital Library can be turned into an information filtering system. This is a copy of my most recent technical interest profile service mail from ACM that said, hey, based on the things that you've built up in your profile, here are some recommendations for newly published things you might be interested in. So all of that technology worked really well up until some time that people started getting onto this internet thing that made overload happen. And that led to so much content out there in discussion lists, in web pages later, in other areas, that simply getting everything that matched the topic you were looking for was still too much. If you don't believe that's true, pick any topic you're interested in, type that phrase into Google, and ask if that was enough. You just read the 600,000 things that come back, and that'll be good. And so the early innovators in collaborative filtering, starting with a system called Tapestry at Xerox PARC, said, maybe what we need is more than just keywords, more than just topics. We need somebody to mark quality and maybe even deal with ideas of taste, of who would like something and who might like something else. And what Tapestry did was provide a manual system where people could actually take these large databases of too much content and mark them up and say, gee, here's something that Gary would like, or here's something that any of our programming staff would like. And other people could come in and put queries in and say, show me the things that these other people thought I might find interesting. In the mid-90s, the idea of automated collaborative filtering and the beginning of modern recommender systems was pioneered. And the first of those systems out there and published was the GroupLens project, which published its work in 1994. And this was automated collaborative filtering for Usenet News. Those who don't remember Usenet News by name or don't use it, it's large categorized discussion lists. And the idea here was that people would rate the articles that they read on a simple scale, usually something like 1 to 5. And you could then get a personal recommendation for which articles you might want to read based on what other people who had similar tastes to you, people who were called neighbors, who had a correlation that was reasonably high with your ratings, had said they liked. And this approach is known as a nearest neighbor approach. Technically, it's known as a weighted k-nearest neighbor approach because you take a certain number of people who are most like you and you combine their individual ratings of things to form a prediction of what your rating would be. And it works pretty well if you have stable tastes, which seems to work in this domain. This is a screenshot from an early newsreader, XRN, that was equipped with the group lens system. At the bottom, you'll see buttons to rate the articles 1 to 5. Nobody ever used those. They used the keyboard to just type 1, 2, 3, 4, and 5. But the most important thing you'll see is on the top, just to the right of center, there are these little bars next to the subject of each article before you get to the date. And that little bar says, here's how much the system is predicting that you're going to like that article. This particular display is from a news group known as Rec Food Recipes, where people posted recipes. And so how much you'd like the article translated fairly directly into how much people thought you would like the recipe. And this particular person's customized rating says, gee, this is somebody who might like, baked potato soup or Swedish flatbread or plum chutney, but not so much mop sauce or minestrone. And actually, it did fit pretty well with the tastes of the person that this was recommended to. And what I should say is that this stuff, even in its early trials, worked really well. So in Usenet, there were studies done by our group here to look at the difference between how well you could predict people's ratings, personalized versus non-personalized. You see some of the numbers on the screen, and the short answer is personalization really wins. But even more important than the fact that personalization wins, people liked it. People used it. If you gave an article a 4 or a 5, people were twice as likely to read that article than if it was displayed with a 1, 2, or 3. And people stayed and used the system more than 12 months after the study was over. Even after we stopped adding people to it, they stuck around because they thought it was useful and valuable. And so that takes me to today, the commercial era, where you see that screen I showed you at the beginning. If you go to a site like Amazon.com, and I should point out, Amazon was one of the earliest companies out there. We took that group lens technology, formed a company out of it. Amazon was one of our first customers, and they were not only using our technology, but developing boatloads of their own to do all sorts of recommendation. And so when you go to Amazon, you can get recommendations based on your entire purchase history and anything that you've given them ratings for as you go. In fact, if you click on one of these and say, why did you recommend Dream Team, that book, to me? It can even come back and say, well, that's because you bought this other sports book. And what they know is that people who like this sports book tended to like this other sports book. And Amazon does a lot of other things within the space as well. You've probably all seen customers who bought this also bought that, which is not so much personalized, but anchored to what you're looking at right now. And folks from Amazon have pointed out it's an extremely useful feature. So, I should add one more here, that Amazon, like so many other sites, now has an extensive collection of customer ratings and reviews, which is just another form of data that, when it's aggregated together, becomes a recommendation. In this case, it's a 4.5-star recommendation that you can dig into more deeply to understand why you're getting that recommendation. This part is non-personalized, but many people find it extremely useful. So we talk about what a recommender is. Just to recap, it's a tool to help people identify worthwhile stuff. They can come in different varieties. Some of them are embedded in filters. So the email filter that takes some of your messages and puts them into a folder called spam or a folder called urgent is a form of recommender. Some of them are recommendation interfaces that say, here are 10 things we think you'd like, or they just place things on the front page of a site hoping that you'll buy them, or you go to a grocery store and as you check out you get a coupon to come back and save $2 on a carton of orange juice, and it's a recommendation tied to an offer or promotion. And some of them, as you'll see coming up, are more prediction interfaces. that really come back and give you a numerical score for the various items that you're doing. And for all of these recommenders, we're going to find the same fundamental challenge. How do we collect the opinion and experience data we need? How do we find and aggregate the right data for a purpose? That'll get us towards the algorithms themselves. And how do we present that data in a useful way? So when we think of recommender applications, there's a broad space of them. I'm going to go through this somewhat quickly so that we have lots of time for the technology, but I think understanding the space of applications is really helpful. And so there are recommenders that are purely editorial, and by purely editorial, I mean that they don't involve any of these technologies. We won't spend a lot of time on them, but there are ones where somebody else gives you the recommendation. There's content filtering, as we talked about in the information filtering and building up profiles. There's collaborative filtering, using the opinions of others, and there's hybrid approaches, and the hybrids mix different technologies together. We can also look at this through different dimensions of analysis, starting with the domain of a recommender. And so what's being recommended? Are we recommending news and information like Google does? Google actually takes other people's input, primarily the input of people who write web pages, but also the input of people who visit web pages, in order to recommend not the search results that best fit the words that are at the top, but the best search results that happen to fit those words. And the difference is, if I look up Minnesota Twins, I will always get the Minnesota Twins website, even though there's some high school student who has a web page that just says, Minnesota Twins, I love the Minnesota Twins. The Minnesota Twins are my favorite team. Here's a picture of the Minnesota Twins. And if you did a simple TF-IDF analysis, that page is more relevant to Minnesota Twins than the official one. Google's figured out nobody cares about that page. No one links to it. Therefore, we're going to give you one we recommend better. You can obviously also recommend products for purchase, and that's one of the more popular domains of recommender systems today, is in the use in commerce. They're also used in education and in other areas. We can look at the purpose for the recommendation. Sometimes recommendations are about actually getting you the content, sales, or information, but sometimes they're about education or building a community. So if you go to an e-commerce site like the one pictured here, this recommendation and the ones here on the right are all about how do I get you to buy something, or ideally, as the examples on the right show, get you to buy more than you were going to buy anyway. But you can go to any of the review sites, the ePinions, the TripAdvisors. They're not really trying to sell you. They're using a recommender technology to combine other people's opinions to educate you in what you're trying to do. And there's some wonderful examples out there that are education or community. OWL was a research system done at the MITRE Corporation whose design, and other systems have now followed this same approach, was to educate people who use software, in this case word processing, about features they might want to learn to use because an analysis of their keystroke patterns showed they have never used this feature, and other people who edit documents much like they do find the feature useful. I had done similar work with people at Autodesk, looking at the AutoCAD package. That work's recently been published in the ACM Transactions on Computer-Human Interaction, showing that you can take commands that people use in CAD tools and build a recommender system out of them by finding commands that are probably good complements to the ones you use, but that don't show up in your log. And people use recommenders even in the space of social networks. One of the earliest examples of these was a system called Referral Web, which was an expertise finding system to help you find somebody in your organization who knew something about a topic you needed to know more about. But what was special about Referral Web is that it also built the social network graph to help you find the introductions to that person, that you had a connection to this person who had a connection to this person who had a connection to your target, so that you could work your way through an organization to get people. We can look at the question of whose opinions are you getting? Are you getting experts? Are you getting ordinary people? Are you getting people like you? Wine.com built their business on the opinions of experts, but there's lots of other wonderful examples out here. Here's an example that's specifically about other people in general just mining out of their postings what good websites were. It's an older system called Folks that in this case is helping people find the best page about Bob Dylan according to a community of Bob Dylan fans. We get to issues of personalization level. You know, does everybody get the same recommendation? So when I went, this is a somewhat old snapshot, I went to Land's End. It knew who I was. I had a cookie on the site. It presented me with an ad for tankinis. Well, in a sense, it's a recommendation. It certainly wasn't personalized. You know, you've seen my picture at the beginning. I promise you I will never wear a tankini. And this is probably a lost opportunity. I was actually remarkably impressed that Brooks Brothers had enough information. I'm assuming when people think Brooks Brothers, they think suit. I probably wear a suit 3 times a year, but I wear a lot of polo shirts, and there it was, something that I would actually find useful. They actually only had demographic information. They were getting information from me from another source that was syndicating content about my other purchases. If I go and see customers who bought this also bought that, that's ephemeral personalization. It's tied to what I'm doing, but not necessarily who I am. And there's lots of examples of ephemeral personalization. The music site CD Now used to let you just come in and say, look, if you want to buy something for you or somebody else, tell us 3 artists you like, and we'll find other music that people who like those artists like. It's not about your long-term tastes. But then what you get at some sites is your long-term tastes. We know everything. We take everything we know about you, and we build it into trying to find things that we think you would like. And that's the deep long-term personalization. Quickly, some other dimensions. There's privacy and trustworthiness. Who knows what about you in the recommender? There's the kind of interface, and I mentioned that briefly before about predictions, recommendations, and filtering. The other issues that come up in interface are whether you make it clear you're making recommendations or you just weave in the recommended products with other things, and the question of input. Everyone loves the idea of explicitly asking people to rate stuff, but mostly people don't. And as a result, implicit input, the feedback that happens when somebody buys a product or revisits a page, does other things that indicate interest, turns out to be really valuable. And then there's a wide range of algorithms. And we're going to move into algorithms in just a minute. So let's start with the really easy ones. We're not going to make it all the way through this list, but we're going to make it about through the 3 most popular algorithms and a little bit beyond that. And the easiest thing to do is to just take summary statistics. Well, what's a non-personalized summary statistic? It's averages, it's minimums, it's maximums. So Expedia had this wonderful feature called Fair Compare that says you're looking for a price on a trip, say, from Rio de Janeiro to San Juan, Puerto Rico. How do you know whether this is a reasonable price? Well, what you'd really like to know is what did other people get as their quote for that trip? I ran this from Minneapolis to Las Vegas, a route I fly a little more often than I fly from Rio, and I get back this chart by date of the lowest price. This isn't a search of what airlines are actually offering. This is a result from what other customers ended up finding when they searched for airline fares. But it's remarkably useful, even though it's not personalized. It's just a summary. The other example of this that some of you may be familiar with is the Zagat guides. These are restaurant guides. They started in New York. They're now widely out there in many cities around the world and some of them that span the areas between cities for best restaurants in a country. And their whole model is really very simple. They have surveys of people who read their guides. They ask you to evaluate restaurants on a scale of 0 to 3 for food, decor, and service, and they ask you approximately what you paid, plus to write a very short review. And they have a secret formula that I will let you in on. The way they come up with these numbers is that they take all of the different scores people put in, they average them, and they multiply by 10. And so if the average is 2.5, a restaurant gets a 25. And people find it remarkably useful within limits. There are people who've been complaining, and I think this has been true for the past 10 years, that the middle ratings in Zagat don't mean as much anymore because the people who are going to Olive Garden say they love Olive Garden, and the people who go to McDonald's say they love McDonald's, and everybody loves their own thing. But they have the data. They could personalize this if people wanted to come in and say, here's enough information about me to match me up with the people that are there. And if they did personalize, what they would probably start with are the most popular collaborative filtering algorithms, the k-nearest neighbor algorithms. Let me start you with user-user. Here's the basic idea. This is the algorithm that was behind the first 3 automated recommender systems and behind most of the early companies in the field. And the story is very simple. Let's say we want to build a recommender system for movies. So we have a bunch of people. They're all sitting around here. Sometimes those people are in a role where they're rating movies. They're inputting into our system their opinion of some movie. And when we get that rating, we're going to store it in a database. And we're also going to compute the pairwise correlations between all pairs of the people in our system. That correlation is a measure of agreement between people. And it's something that's very easy to maintain and incrementally update as you go. Now, once we have that pairwise correlation table and we have the ratings, we wait for somebody to ask for something. So somebody comes in and makes a request. They might just say, find me a good movie, or they might say, what am I going to think about this particular movie? When that request comes in, the first thing we do is we look at those correlations to find a good neighborhood. Who are the people who are most like, in their past opinions, this person who's asking the question? Once we have that neighborhood, we can look up those people's ratings. And our collaborative filtering engine really does just 3 things. It takes these ratings and normalizes them. It weights them by the correlations, and then it combines them and denormalizes them back to the user scale. And when I talk about normalization and denormalization here, it's a compensation for the fact that people have different levels of positivity or enthusiasm. What we learn when we run these systems is that there are some people who everything is a 4 or a 5. A 4 means it was okay, and a 5 means I loved it. There are other people who've never actually gotten to the number 5. Most things are 2, and there are a few 3s and a couple of 4s. And a 2 means it's okay, and a 3 means, okay, I guess I might spend money on it. And a 4 means this is wonderful, but I've never seen anything better than that. And if you don't make your adjustments, it's really hard to match somebody who thinks everything's wonderful with somebody who is the other side, who's saying, I think everything's pretty miserable. But if you normalize, you can usually match those people if they at least agree that the most wonderful things are about the same. So I realize some of you don't go with symbolic things. You'd prefer something a little bit more, letters or numbers. So here's a table for the same idea for this computation. So let's put me at the top here, and I'm trying to decide which of 2 movies I want to watch tonight. This is a very small, compressed piece of what would be a much larger matrix. In the real world, this matrix would be very sparse. Most people may have rated well under 1% of the potential products that a company has available. If it's Amazon and books, most of us have rated maybe 1/10 or 1/100th of 1%. But I'm pulling out a little dense subset of this matrix and saying my first job is to identify neighbors. So Susan's not real helpful. Pat would be a really good neighbor except for one problem with Pat. Well, let me actually take it through. The easy neighbors here are Ben, who mostly agrees with me, not exactly the same, but mostly agrees, and Nathan, who, again, mostly agrees with me. John is an interesting case. John disagrees with me, but consistently. And so it might be in many domains I can say, well, if John likes it, then I won't, and vice versa. And then there's Pat, who is this so much like me that Pat hasn't seen these movies either and is not going to be useful. And once I've identified my neighbors, Ben and Nathan on the positive side, John on the negative side, I can just work my way through each column and say, well, look, blimp. Somebody who has taste like me thought it was very good. Somebody opposite me thought it was pretty bad. That's a pretty good sign. Rocky 15 I don't have a lot of data on, but what data I have is not promising. And from that and much more data like it, I can make a decision. Now, if you build this into a system, you get a system like our Movie Lens system. It's free. It's available for the public to use. It's at movielens, movielens.org. And I'll give you a very quick tour of what this looks like, but if you want to explore it, we've had probably about 150,000 people using it, and some of them find it really useful. Some of them just take a look at it and decide they don't need a movie recommender. But if you log into Movie Lens and you've gone through the process of rating at least 10 movies to get started, you come in and the first thing it says is, hey, look, here are some movies you might like. New movies in theaters, new movies on DVD, or you can search. If you want to search, you could search by attributes, you could search by name, and it will come back and just give you ranked lists of here's what we think you're going to think of these movies, and more information for you to do your own research, and a place for you to come back and say, well, actually, what I really think of the movie is something different. Anytime you update this score, that's going to lead to an incremental improvement in our ability to predict which movies you're going to like. And you can search through and find movies that match one criterion or another. I know that anybody doing recommender systems gets involved with matrix math, so if you look up matrix, there turn out to be some movies about it. I was looking for the matrix inverted, but that one I don't see here. We'll move on. And we even added features, for instance, if you wanted to go out to see a movie with 2 or 3 other people, we can find movies that a bunch of your friends will all like to help you find those movies. So one last thing, because this algorithm is really important. We want to understand the idea of collaborative filtering for a target user. You need a distance metric that tells you how far apart that user is from other users. You create a neighborhood of the people who are close by. You take the ratings of the people who are close by, do that weighted average, and you get back a prediction. So all of that sounds wonderful, but there are some problems. There's a problem in sparsity that you just have so many customers, and many customers have no relationship with each other. Whereas most products do have a relationship in a typical business that might have millions of customers but only thousands of products. You also get a problem of synonymy, that sometimes different products really have a relationship that's not there, so, or not expressed through the ratings. So if you have skim milk in your market basket, if you go through traditional collaborative filtering, there's a good chance it might come back and say, hey, you know, people who are like you like whole milk also. Well, that's probably not that useful. Or if you have, you know, one brand of legal pads, we don't want to recommend another brand of legal pads. And for that reason, many collaborative filtering systems have moved towards an item-item model, where you have all of these items, and again, you compute a distance function between them. And the distance function that we use to create that item neighborhood is typically the distance function of how much these items are rated similarly by different users. So this matrix we have here is the same user by item matrix. Before, we were using that to take a look and say, what users are like me? In an item-item algorithm, we say, what items are like this item? By seeing which items are treated similarly by different users. And one benefit of that is you can do that with 0-1 data, or even purchase, didn't purchase data, so that we can look in a whole bunch of market baskets and find, wow, there seems to be something here that says, not are these purchased together, but do users tend to think of these things in some way that's similar? So do we have some relationship that, yeah, ribeye steak and sirloin steak, they seem to fall in the same being similar, whereas ribeye steak and fish may not. Once we've built this matrix, we can take a target item, take its most similar item neighbors, and again do a weighted average of the individual users' rating for those closest neighbors. And in essence, what we've now done is we say when we make a personal recommendation for you, we do it by finding items that are close to the items you've already rated according to other people in our system. It turns the computation upside down, but it actually works remarkably well, and you could do this by regression. You could do this by a simple weighted sum, and in either case, you get a prediction of what the person would like. This has now become probably the most popular algorithm in commercial recommender systems. It has good quality. It has a huge performance gain because things are stable and they're typically done incrementally. But if you're looking at the trend, and I'm just going to give you a quick pointer towards that trend, the trend these days is in dimensionality reduction algorithms based on ideas like singular value decomposition as a technique that was used by the information retrieval community. And I'm not going to take you through all of the gory details of it, but the basic idea behind these dimensionality reduction algorithms is that you take a matrix of ratings and you compress it down to a much smaller number of taste dimensions. So instead of saying I have 30 million customers and 15,000 products, I must have 15,000 possible things people could have taste on. You compress that down to perhaps 50 or 100 dimensions of taste, and then you express each customer and each product in terms of that taste space. And once you do that, you can actually directly predict people's liking for a product based on whether the taste matches up. And there are all sorts of computational issues there that we're not going to get into. What I want to do as we move towards questions is first just point out that there's a lot more here from the spaces of machine learning, from the space of AI more generally. Different people have applied graph algorithms to recommender systems and collaborative filtering, clustering techniques, rule learning systems. And in fact, the most popular recommender systems in commercial use today are almost always hybrids that mix together different methods. This was something that was in the news quite vividly when Netflix issued the Netflix challenge and gave out their $1 million prize to a large team that brought together a bunch of different methods for combining machine learning approaches to do the best job they could predicting which movies people would like. So I'm going to give you a set of resources for further information. There are some wonderful survey articles that are out there. I'm going to point you to a couple that came from our group. These links here, these URLs are all places where you can get the actual article directly. We have another one that's coming out next month in IEEE Spectrum that's a very high-level overview for people who want to hand their boss, their manager, something that says, here's what recommender systems are about. You can look for it in the October issue. There's a couple of books, neither of them ours, but they're both pretty good. Recommender Systems and Introduction is probably the best place for people who want a starting point. The Recommender Systems Handbook takes you through lots of the gory technical details. And then probably the most important thing for people who might want to use these are the software tools. There's Mahout that's out there as part of the Apache open source work. There's also a toolkit from the MyMedia project in Europe and LensKit from our own group. Each of these has multiple machine learning recommender system libraries built into them. You can examine the code. You can see how it works. You can build them into applications. None of the three really has the performance to go to something commercial strength. There are plenty of companies you can get that from, but they'd all work perfectly well if you're talking about things in the size of tens of thousands to get a prototype up and running. So with that, I'm delighted to have had a chance to talk with you a bunch about recommender systems. My understanding is that we've got a bunch of questions, so why don't we move straight to the Q&A?
Okay, thank you, Joe. A lot of questions, and we'll see how many of these we can get in. Here's one that's sort of timely. Have recommender systems or recommender algorithms been used to guide voters or parties in elections?
That's a great question. I think they've actually been used the other direction. So not so much guide. There have been some systems out there, and one of the public radio stations actually did a find a candidate, find an issue recommender where you would go in and answer a bunch of questions about what you felt on different policy issues, and it would point you to candidates whose positions or actions matched that. I don't know that it ever got any heavy, serious use, but recommenders are used what we sometimes think of as backwards to identify the people that are likely to be most receptive to a message or product. We had some commercial success doing this with surplus merchandise, who might need a DVD player right now. But I know that type of technology is used by political parties to try to figure out where to target people who are going to come knock on the doors and talk to people, or mailings or other things, to try to figure out who's likely to be an undecided but movable voter. So yeah, these technologies are used in different ways. They're obviously not used, at least in countries I know of, with the actual vote data. It's not like we come back and at the end of the election say, gee, based on the fact that you voted for so-and-so, we think you might be interested in this. I think people would be a little creeped out if their votes were used that way.
Yeah, certainly. Okay, a question about Movie Lens. How does it compare to some of the other movie recommender algorithms, such as IMDb, Flickster, Gini?
So I think there's two pieces. There's the algorithms and there's the system. The big difference between Movie Lens and the other things out there is probably the nature of the system. That Movie Lens is very much a simpler research system. It doesn't have all the connections to either renting the movies or places to buy them or buy tickets or anything else. It has no advertising. It's not commercial. Internally, Movie Lens uses an item-item recommender algorithm, which is probably not that different from others that I know that are out there. And I don't know what IMDb has. I know Netflix has fairly similar algorithms. It also has a bunch of experimental recommenders going at different points. And so one of the things that we've done a lot of lately is tools to help you explore movies through tagging, so that you can come back and say, here's a movie that looks really exciting, but I'd really rather have a movie that wasn't so depressing and come back and say, can you give me a movie like this but more in one dimension or another? Can you give me a movie that's sort of like this but rated PG or lower? Can you give me a movie like this but that's more of a comedy? And as we add those kinds of features, and we do them to explore what you can do, we work really closely with our user community and get feedback to try to understand what's going on. But from a technical perspective, the basic core of recommender systems that's out there is very simple. The things that make particular businesses much better at this or much worse tend to have to do with gathering data and with pulling together different kinds of recommendations in a usable interface.
A couple of related questions here about sort of the fact that it seems like these systems treat users as kind of a stable, static thing, but individuals have multiple roles. They operate in different contexts. They change over time. How do recommender systems adapt to changes in context, changes in roles, changes over time?
That's one of the great challenges right now. In fact, the Recommender Systems Conference that I just came from a couple of weeks ago in Dublin this year, one of the big themes in the workshops at that conference was on context-aware recommendation. There are a bunch of people who are doing this by trying to build things like seasonality and other context into recommender systems. Lots of people have looked at trying to age old ratings and old preference information to recognize things that are inconsistent with your current preferences. But the reality today is that many systems do that rather poorly. Mostly the ones that do it well do it by giving the user more control. So if you go to Amazon and you buy something as a gift, there's a way to say, don't put that in my profile. You know, just because I went out and bought a Barbie doll for my niece doesn't mean I want recommendations for Barbie dolls tomorrow. And what we're seeing is a trend towards giving people more control, more visibility, but we're certainly at a stage where it's more of a research space problem than a solved commercial solution to deal with context and recommendations, roles other than by having multiple accounts or explicit representation, and I think most generally change in interest. If your interests change all the time, it's hard to deal with a recommendation, but if your interests change gradually, we'd like to be able to model that and have the recommender keep up with you and ideally even stay one step ahead.
You classify this as one of the kind of big unsolved current research problems. What are some others that are out there? What's kind of driving the research community in the recommender space?
There's a number of them. There's this broad question of how do you come up with recommendations that are fundamentally more useful. And that comes from a bunch of things. I'd noticed there was a question somebody asked about diversity. There's been a lot of research specifically looking at how do you make sure that you're not giving somebody a small set of items that are all too similar to each other, yet we know that typically if you diversify too much, you end up with things that people don't like as much, and trying to balance that is a challenge. On the algorithm side, people are very interested in both performance, computational performance, coming up with good parallelizable, distributable algorithms that can deliver real-time performance on large sets of data, especially in the dimensionality reduction areas that I talked about. There's a lot of interest in trying to improve the quality of the data itself. How do you know when to believe people's recommendations? And just to throw one more example out there, there's a huge area that's looking at the integration between social networks and recommender systems. There's some work there that shows that people are more likely to believe a recommendation if it's based on opinions of people they know and trust. On the other hand, there's a lot of data that suggests that with a large anonymous group of people, you can actually do a better job finding opinions that match your own. How do we resolve these two and come back with, a mix between recommendations that are good and recommendations people will trust?
There's a question about have recommender systems been used in the area of health?
Yes, they have. I've been recently at some of the health informatics conferences, and there's a couple of areas where this is coming up already. There's work being done on recommendations in health for particular things like goal setting. People who are going into an exercise program where they will get recommendations on what the next goal they might want to do, recommendations in diet and exercise. It's still a very early stage area. There's a lot of research. We've been working with people with medical informatics and medical school people looking at recommending health and medical literature to patients who've gone through diagnosis. What can you offer them that might be appropriate for them to read to help them manage their own care? There's active workshops coming out all the time on recommendations and persuasive technologies for health management, and I've seen them in everything from diet and exercise to smoking, alcohol, drugs, sex, other areas where people are beginning to take the basics of recommender systems to try to guide people towards healthy choices.
Okay, there's still a lot of questions we could deal with, but we're running out of time. Just to let people in the audience know that we are keeping all these questions in our system, and we will try to answer a number of them offline after the webinar is over. So just because your question didn't get asked live doesn't mean we won't respond to it. Okay, this webinar will be available on demand at learning.acm.org/webinar/recommender. And don't forget to check out ACM's other great learning resources in the area of recommender systems, human-computer interaction, and related areas. In closing, I'd like to once again thank Dr. Konstan for his informative presentation and insightful answers to the many questions we were able to get to. And a special thanks to the audience for taking time to attend and participate today. In conclusion, we'd like you to take a few minutes to fill out our survey. It should only take you a couple of minutes to do, and it'll help us improve our next webinar offering. Please check acm.org and learning.acm.org in the coming weeks for announcements of other upcoming webinars. This is Gary Olson saying, hope you can join us next time. And if you have any ideas for future topics or speakers, please email them to learning@acm.org. Thank you.